Okay, let's continue. So previously we gave you strong duality and tried to convince you that the primal and the dual linear programs, their optimal solutions will have the same objective value. That's cool. But then when I say they are equivalent, you probably have a question. Is that if I solve the primal program, yes, I get the objective value of the dual program. But how may I get a dual optimal solution? May I get them directly, or do I need to solve the dual program? Well, the answer is here. If we can solve a primal program, then the dual optimal solution will be directly obtained, like this. So the statement is here. For a linear programs defined here, suppose that we have an x bar, which is primal optimal. Then at the same time, we would know its basis B. And we know that it's true because when we solve a problem by a simplex method, we will keep changing basis, right? And when we stop, we are still at a basis. So there must be a basis that we may use. And then when we have that basis, we have a formula here. It says that if you calculate CB transpose AB inverse, then that particular vector would be dual optimal, where the two elements are defined as following. CB is a m by 1 vector, and that is the row 0 vector of all the basic columns in B. And then AB is a square matrix, which is m by m. That is from row 1 to row m. And again, for those columns that are basic. So the proof is also not very difficult, but we don't want to talk about it because I don't require you to understand. If you want to know, ask me. But instead, I'm going to give you one example to illustrate this idea. So suppose we have a pair of primal and dual programs. You may want to verify that they are indeed primal and dual pairs. And then let's try to solve the primal first. We have the standard form for the primal by adding slack variables and set them to be non-negative. So I have a C transpose and A here. This C vector is the vector for objective coefficients. For x1 it's 1, for x2 it is 0, blah blah blah. And for A is the coefficient matrix, so it's 2, 2, 1, 2, 2, 0, negative 1, 1, and the identity matrix for slack variables. And also, by default, we say a vector is a column vector. That's why here we do a transpose. Okay, so later I'm going to solve the primal linear program and then to obtain a dual optimal solution. So the first part is easy. We have the initial tableau like this, and then we may do some simplex iterations, blah blah blah, and eventually get an optimal tableau. Actually, this has been done. This example has been solved when we introduced a simplex method 2 weeks ago. Okay, so now given that, we know there is a so-called optimal basis, capital B, that contains 1, 2, and 5. Okay? The set of basic variables. The primal optimal solution for the original problem is x bar, which is 3, 2. The values for x1 and x2. And if you plug in that into the original objective function, you get z star, which is 3. That's okay. And now I'm going to construct the dual optimal solution according to the formula I just mentioned. So I'm going to take a look again at C transpose and A. They have nothing to do with my optimal tableau. Okay? When I formulate the primal program, I get these values. But now I need to use my optimal tableau to get XB, and XB are the variables in my basis. Then I'm going to take column 1, 2, and 5 from C transpose and A. For column 1, 2, and 5 here, I get 1, 0, 0. That's my CB transpose. For columns 1, 2, and 5, I collect them into my AB matrix. Okay, that's why you see this matrix. That's why you see this matrix. It directly comes from column 1, column 2, and column 5. So I take the original tableau or the original formulation, but take a subset of them according to my optimal basis, and then get these two elements. Then according to my formula, I can calculate CB transpose, which is already there, and AB inverse. I do the inverse of that AB matrix to get this, and then immediately we get 1/4, 1/4, and 0. So that's a dual solution. We may try to ask whether it is feasible and whether it is optimal. So first, it is feasible, because you may plug in this solution back to all the dual constraints, then everything will be satisfied. And you also see that they are non-negative, so that's good. And to see that it is optimal, we don't need to solve the dual program, because all we need to know is strong duality. We may plug in this solution into the objective function. We're going to get 4 times 1/4 and 8 times 1/4. We're going to get exactly 3, which is exactly Z star. Then, given that this solution is dual feasible, and its objective value is the same as the primal optimal objective value, we're done. Y bar must be dual optimal. Okay, so this is just a simple example trying to convince you that if you solve a primal program, then you don't need to do the same process for your dual. All you need to know is to get that formula and get some related information, plug into that formula, and then you get your dual program. If you need to run 1 million iterations to solve your primal, you don't need to do that for your dual. You basically just need to do one matrix inverse and do some multiplications, and then you get your dual solution. So primal and dual are really equivalent in a sense that if you solve one, you get the other solution. If you solve the primal, you solve the dual. If you solve the dual, you solve the primal. They are just equivalent. Our last property about primal dual pair is called complementary slackness. Okay, complementary slackness. So let's introduce the idea. Suppose I have a dual program, which is minimize Y transpose B subject to Y transpose A less than or equal to C transpose. Suppose that's the case, then I can subtract Y transpose A by the slack variables W transpose. And then I say all of them should be non-negative. Okay, what does that mean? That means I am using the W variables to fill the gap between the left-hand side and the right-hand side of the dual constraints. Then I get some properties of W. If I have a primal problem defined in 1, which is the pair we just mentioned, which is the standard form, and I have a dual defined in 2, okay, it's not exactly the dual of a standard form, but we know they are equivalent. Then we have the following: X bar and Y bar W bar or Y bar W bar. They are primal and dual optimal if and only if W bar transpose times X bar is 0. So what does this mean? X is primal solution. Okay? If your primal problem have n variables, then you know in your dual program you have n constraints. Okay? And each constraint has one slack variable. So the dimension of X and W are the same. So that's why they can do an inner product. And also because in your standard form X bar is non-negative. And here we also require your slack to be non-negative. So each individual elements are non-negative. If you have a lot of pairs of non-negative variables multiplying each other. And then what will you have? If you have a 0 as the sum of the result of inner product, that actually means Wi times xi must be 0 for all I. Okay? For each pair of Wi and xi, if one is positive, the other one must be 0. That's the result. Okay, very quickly we can try to prove it. So first we know we have C transpose X bar, which is Y transpose A minus W bar transpose times X bar, because C transpose is this guy. Okay, and then in that case, we have Y transpose A X bar minus W bar transpose X bar, which is just to split the product. And then A transpose X, AX bar is exactly B, so we do one more derivation. And now, suppose we know W transpose X is 0. What does that mean? That means your C transpose X and Y transpose B are the same. So then if X bar and Y transpose and Y bar and W bar, they are primal and dual feasible, and then they are primal and dual optimal. Okay, and you can see the result is if and only if. Yeah, so that's the basic idea. As long as you have this condition, then that's going to imply that your objective values will be the same. Okay, so as we mentioned, the condition here actually shows us something about dual constraints and the primal values, primal variables. If a dual constraint is non-binding, that means your W is positive. Then the corresponding primal variable must be 0. Or if you have a primal constraint that is non-binding, then the corresponding dual variable must be 0. Okay? So you may want to ask, well, that sounds to be true, but why do we want to know that? There are some reasons that we will mention when we give you exercises. Okay, so quickly summarize, why do we want duality? Those properties we just mentioned provide some reason. So given a linear program, we may solve it directly, of course. Or we may solve its dual and then get the primal optimal solution, right? As we just mentioned. So you may want to ask, well, why do we want to do that? One reason is that the computation time of the simplex method is roughly proportional to m to the power of 3, where m is the number of functional constraints. Why is that? You know that in each iteration, you basically get a set of variables and say they are basic, right? And you will do that after you get an m by m linear system to solve. And to solve a m by m linear system, that is roughly to get its inverse, which requires m to the power of 3, or roughly. So this turns out to be the bottleneck of solving linear programs. So you really care about the number of functional constraints you have. But on the other hand, for variables, you do not care about them too much. So that implies if you have a problem where you have some variables but much more constraints, then solving the dual program can actually save your time in many cases. If you are not too unlucky, then as long as you revert the constraints and the variables, you're going to have a lot of variables but much smaller number of constraints. That's going to help you in using the simplex method to solve your programs. And actually, that's just one benefit. There can be some other benefits of knowing duality. For example, duality helps us to understand the sensitivity of a linear program, which we will introduce, and many more. So, if you have some free time, I suggest you to read related sections in the textbook carefully And if you are able to prove those theorems we just mentioned, that would be wonderful. But if you cannot, we still need to know how to apply them. And then we will do some exercise on it. Thank you.